going?
Hello.
Awesome. Really appreciate you presenting this year.
Oh, look, you're very welcome. I've had a lot of fun putting this one together because all of my presentations previously have either been to professors of mathematics education or to people in India. So this is my first voyage to North America
Awesome.
to give you more mathematics content than I would usually share, because my primary expertise is history, and I've been researching the history of mathematics from Latin, ancient Greek, Sanskrit, Arabic, Hebrew, French, German, Italian, Russian, Dutch, Czech, Spanish, Mandarin, all these languages. And it's really by exploring the different cultures and looking at thousands of documents and original sources that I've really been able to pull together a completely new approach to pedagogy. And I'm not going to go into the history in this talk, but I've got lots of other presentations, videos of lectures I've given and PowerPoint slideshows that you can download from my website, which is just simply podometic.com. You'll see that mentioned during the slideshow. And I'll also just mention that I'll be making this slideshow available for download from my website. And this is currently recording, so it will be made available on my YouTube channel, which is just my name, and also I guess on any other YouTube channels as people see appropriate. Okay, so it's gone 6 o'clock, so I'm going to kick off and start the show. The topic is why math education must be black and white. And so I thought I'd start off with a couple of black and white photos to introduce you to the theme. The photo on the left that you've probably seen for the last few minutes is me sitting at the bottom left front row in 1968, when I began to argue with teachers about the explanations of mathematics that they were giving. So at the age of 7, I argued with my primary school teacher, my grade 2 teacher, about her explanation of multiplication. In my opinion, it made no sense whatsoever, and I thought that my teacher was mistaken in what she was saying. And yet I didn't know my times tables at that time, so my teacher in grade 2 won that argument, but later on that became my first peer review published paper on how the understanding of multiplication at that time had been wrong for 398 years. In short, people have been quoting Euclid as having a definition of multiplication, which is repeated addition, and it was nonsensical. And I went into that, and I noticed this when I was 7, and that really kind of got me into wondering about what else might be wrong about what we believe about multiplication and other basic operations on the integers. Because Euclid never defined multiplication as repeated addition, even though that's what many mathematics education professors say he did. He never did. So anyway, there I am on the right-hand side. And as you can see, 20 years later, I was starting to be written up in newspapers. And if I just lean back a little bit, you can see that one of the quotes in the newspaper was my statement, "I hope to change the way the Western world teaches maths." And if you didn't see that in the article, it's just there as well. So I made it my goal, believe it or not, to fix mathematics education in 1983 in March. And I wasn't really sure what I'd ever achieve, but I've had this goal of really fundamentally changing our understanding of the foundations of mathematics for over 30 years that I've been working on this project. So Now, what I'm just wondering, I might just let you read these slides rather than read them to you. So I'll just give you a moment, and I'll be quiet to give you the opportunities of reading these to yourself. So that's why math education must be black and white. When people are asked to explain, for example, multiplication, we get many different responses about what multiplication is, but typically we're given applications of the principle of multiplication as opposed to the actual foundational idea of what multiplication is. So I'm going to be saying, how can we bring about a complete black and white approach to explaining the foundations of mathematics? So instead of having fuzzy explanations where we've got lots of different ideas to try and reveal what a concept is about, I'm wanting to be a little more precise in the foundations. So how can we make our mathematics education black and white? Well, we can start off with our number words. So one of the comments here is that maths foundations are about counts, measures, and relationships between quantities that reveal predictable patterns. So let's just look at one of the most predictable patterns that we have in early primary elementary level education. So we just go 90, 80, 70, 60, 5t, 40, 3t, 2t, and 1t. Now, you're saying right now, hang on a second, Jonathan, you're wrong. That's not the number words that we use in school. But I'm saying that what we need to start to do is to apply the logic of mathematics and the patterns embedded in the structure of mathematics in the way that we talk about mathematics. And for those that are interested, the suffix t, ty, denotes 10, and it's actually in the Oxford English Dictionary. So if Miley Cyrus can invent a new word or make it popular in twerk, we should be more confident about being flexible with the number words that we use with children in primary school. So if we were to ask a 5-year-old, what's 10 plus 20, that 5-year-old will struggle to answer. But if we ask a 5-year-old, what's 1t plus 1t, they'll often, 1t plus 2t, they'll often say 3t. So if we give children the right base 10 word structure, then the children will start to enter into their own understanding of mathematics, where base 10 and positional notation is embedded in the words of mathematics that they're using. And this is not a new idea. I've found this in some maths books over 100 years ago. People were suggesting these approaches, and yet they haven't really bubbled to the surface yet. So if we look at the actual number words, we see the current situation, and we have, for all the teens, we have the place value is reversed, and 18 is often confused with 80, 19 is often confused with 90, and so on. And the numbers like 12 and 11 really have no connection with base 10 logic at all. So again, in the early ways of getting children to understand what's actually going on with the number words, we can simply use the logic embedded in the mathematics as developed by Aryabhata around about the year 500 CE. So if we went up, we could go, in fact, I'll just go back onto the previous slide. If we go up, say from 14, 15, 16, 17, 18, 19, 10, children are searching for patterns in the number words, and so for the number 20, they may well come up with 10, which is perfectly logical to them as they struggle, and then we'll say, no, 10 is actually 20. And so the child's formulation of the number word is more logical than the use of 20. So we've got 1T for 10. It's an alternative. We can use 10 or 1T. And then we simply use the base 10 structure of 1T1, 1T2, and so on. And people will be possibly quite familiar with the Chinese number word approach. And the Chinese children at age 6 can usually count much, much higher than Western children at the same age, because for their 11, they use the number word 10-1. So 10-1 plus 10-1 is 2-10-2 in Mandarin. Very, very simple. And it's not the only reason why the Chinese are good at mathematics, but it certainly helps get children off to an early start. So if we ask a 6-year-old, what's 1T1 plus 2T2, they'll often say 3T3. And 1T1 is a better number word to use in the early ideas, say at kindergarten and grade 1 perhaps, than 11. 11 has no connection with a 10 and a 1, and what we're doing is we're making base 10 explicit. And this is all on the theme of making mathematics education black and white, making it absolutely obvious what is going on. So another way that we can get our maths education to be a little more black and white is with an understanding that many, many people say that mathematics is a language. Well, in that case, we better understand the grammar of mathematics. So if math is language, it must obey the parts of speech of language. And yet we teach in Australia, where I'm from, we teach grammar, the parts of speech, usually around about grade 3, sometimes into grade 4. And that's the ideal time to incorporate it into our basic arithmetic instruction as well. And I'll give you some examples. So if we look at the grammar of elementary math, I'll ask adults a question. I'll often say, what's -7 minus -4? And when I ask people this question, I'll often say, what do you think your neighbor would answer to this question? And that usually gives people permission to have a go, because if they're wrong, oh, it's what their neighbor probably would have answered and not them. So I never ask people directly questions. I usually say, you know, what do you think that shop assistant would say to -7 minus -4? And nearly all the time, most adults answer -11. And the reason they would answer -11 is that they are confused with, is it like 2 minuses make a plus? They're grasping at the rules that they memorized at school, that they memorized with no actual meaning of what's going on. And so let's have a look at the reason why this is problematic. Negative is an adjective, 7 is an adjective, the minus is a verb, negative is an adjective, and 4 is an adjective. We've got something which doesn't obey the structure of human language because there are no nouns. So it's no surprise that if we have a language which is with the nouns are missing, then we're going to be totally confused. So we can do this as an example. We can ask the same person, what's 7 negatives minus 4 negatives? And every child I ask that question answers 3 negatives. Why? Because we've put the grammar back in by using nouns in the question. And 7 negatives minus 4 negatives is really child's play because there's nouns put in there. And yet we're just totally oblivious to such simple maths hacks that are available to us. And so the answer, obviously, is the fact that 7 is an adjective, 7 negatives. Negatives are nouns, and one of the clues is that they're plural. So when you have something which is plural, it's more often than not going to be a noun. So we've got adjective, noun, verb, adjective, noun. And that semantic structure is very, very simple for children to start to explore across both positives and negatives. So my recommendation, and what I do in India, is I teach negative numbers and positive numbers to children in grade 1 and 2. And they have absolutely no problem dealing with negative numbers. So the parts of speech simplify parts of maths. Sorry, I said maths then. Naughty Jonathan, it's math where you are. So here's a kind of a template for the grammar of the terms in an addition equation. So I'm using the formal terms. So in schools, we usually kind of blur things a little bit. We might just talk about summands, we might talk about addends, but the first number in an expression in addition is called the augend. You might not have heard that, but that's what it's called. And sometimes the augend is an important concept because it's very important that you build the first floor of a house before you build the second and third floors. So sometimes order does actually play a role. So we've got adjective nouns. So we've got the augend is an adjective counting a number of noun units. We've got the verb of add and adding. And then we've got another adjective, which is another number of units being added. And that results in another sum, an adjective, a count of nouns. So if you start to be aware of what's going on in equations, you can start to see them more as a game. Imagine if we were playing netball. For example, we've got a ball, we've got a net. So we've got nouns, but there's no game to be had in netball until you start to run, until you start to throw. So in all games, we have nouns, but we also want to have the verbs, and that's when mathematics starts to become dynamic rather than static on the page. And if you can get children to imagine the movement in the mathematics, they're going to start to be able to pay attention and enjoy the stories behind the expressions and the equations. So here we've got multiplication. So we've got the formal terms of a multiplicand, which is an adjective describing a count of units, the initial number of units. We then have a verb, and the multiplier is an adverb, which is describing, in the case of repeated addition or repeated subtraction, the number of times the multiplicand will be either added to 0 or subtracted to 0. Now, you may not be familiar with the use of 0 in multiplication, but I'll be going into that a little further on. And we can see that in the grammatic structure of multiplication, that the product is actually an adjective, a count of units. So you can use the formal language of grammar, but I think it's also more important really just to focus on what are descriptive numbers which describe counts of objects, what are the actions, what are the operations that we're actually doing as a verb, and what is the end result. And I'll just mention that I'm kind of giving you a taste of what I've been developing over the last 33 years. I could probably talk non-stop for a week, but this is kind of like a sampler off the smorgasbord of some of the ideas to share with you. So I'm not going into all of them. I'm just giving you a bit of a taste of the various components. So math education must be black and white. How? Well, what about freedom from British arithmetic? which is built upon Greek foundations, typically from the ideas of Pythagoras and Euclid and Nicomachus and so on. But the British mathematics foundations were based on ancient Greek foundations, which didn't have a concept of zero. Number one wasn't considered a number either, and they definitely had no concept of negative numbers. So the British maths that's been around pretty much for the last 500 years has been really built for 1, 2, 3, 4, and so on. And it's simply not fit for purpose. We have a totally different understanding of physics in the world today. And we have an understanding that negative quantities and positive quantities are equal and opposite, in the way that, for example, one positron, which has the positive charge, and one negatively charged electron, a positron and an electron meet each other, they cancel each other out, they release some energy, and they sum to zero. So we can make maths a little black and white by moving on from the Greek foundations of mathematics, which were 1,000 years out of date when the Indian mathematics came along. So the Indians really cemented their understanding of zero and positive quantities and negative quantities in the 7th century. And the Greek foundations that are still in the textbooks today are from the 4th century BC. So it's a little absurd, but it's also a function of a colonial past in which the British believed that the Earth was only 6,000 years old, possibly less, and therefore any culture which had any science or knowledge dating back beyond Adam and Eve simply had to be erased from history. The other aspects too, the Western churches, they thought that zero was the void and the realm of the devil. And when the Indians were talking about infinity, that was sacrilege because only God was infinite. So you had religious ideas coming in with the British Empire as they sought to take Greek philosophy and Greek ideas of mathematics and the prestige of philosophy around the world. But there are often cultures that had better ideas when it came to mathematics than the British, who really didn't invent any fundamental mathematical foundations. They acquired them from other cultures. So as you can see from this slide, Bharat is another word for India. And this color scheme is based on the Indian flag. And the mathematics from India from the 7th century was built for zero, and the symmetry of what we would consider the real number line summing to zero. So from zero, you've got one positive on one side and you've got one negative on the other side. You can see I've got the negative sign on the opposite side of the number to just show the actual symmetry from the zero. Again, this is just a bit of a taster, but I hope to give you some cool ideas. So this is my last tour of India. This was my 3rd tour. I was meant to be in India again on my 4th lecture tour, except coronavirus came along. So you can see the sort of the crazy path that I go throughout India, and I'm visiting a lot of schools. And on this trip, I also went up north into Nepal and gave a lecture in Kathmandu as well. And these people are very keen to reclaim their cultural heritage that was pretty much taken from them by the implementation of the Macaulay education system of the British, where they really said that all local customs and cultures and knowledge systems had to be replaced by what the British deemed was appropriate learning. So as a mathematician, when I go to India and I say, hey, guess what, India, your mathematical foundations are superior to those that came through the West, it's no surprise that I have hundreds of people queuing up for autographs after I visit them in schools. And I often find myself unexpectedly on billboards in India as well. Maybe it's a bit of the oddity that there's a Melbourne guide traveling in India explaining how mathematics works when India invented it in the first place. But nobody in India is aware of the insights that I've acquired over the last 30 odd years. And you might have large classrooms, but I assure you, your classrooms are not as large as the ones I have in India. In this particular classroom, I had 550 students come to hear me give an hour and a half lecture on mathematics. And it's nothing for me to give a 2-hour lecture to school children on mathematics. And they pay attention, they are perfectly well behaved, and they are model students. And for children in India, education is a prized possession, and they treat it with great respect. And I think it's a credit to them that they do treat their education so seriously. Unfortunately, there's probably about 5 million, or maybe even more than that, genius children in India, little prodigies who are too poor to go to school, which is a crying shame. Okay, so arithmetic is based on ancient Greek ideas, and it arose before India invented zero as a number. And my pedagogy I call Podometic, which is an update on arithmetic. And Podometic is my pedagogy of Bharatiya maths, which is Indian maths. And it's based on the ideas of Aryabhata, who first documented a 0 and a base 10 place value system, and the writings of Brahmagupta, who first documented positive quantities, negatives, and the 4 fundamental operations, and much, much more. So here, for example, is Aryabhata's place 10 system, and I've just added a little bit of fun color to it. So you've got the Sanskrit word for 1, which is eka, and then you have 10 eka, and it becomes 1 dasa. You have 10 dasa, it becomes 1 sata, 10 sata, and then it becomes 1 sahasra, and so on. So this system, you can see that the number groupings is a little different to the West. There are cultural differences in the words. This is in Sanskrit, it's not in Hindi. But there are so many wonderful things that we can do when we incorporate color into our concepts. Because guess what? If you've got 2 blues and 2 yellows, that's the shortcut fun way of talking about quantities as well. You'd have 20,020. So you've got all of these wonderful, sorry, 20,200. You've got all of these wonderful concepts where we've gone through centuries of printing textbooks in black and white, and yet the ancient Indians used colors as variables in their problems that they needed to solve. And other cultures have used colors as well. And going back to even the 2nd century BC, the Chinese gave positive numbers red rods and negative numbers black rods. So we can certainly bring in more color and fun. And when I talk to young children, I actually teach them through cartoons. So I'm writing a series of mathematics books, which are all just cartoon storybooks with animals. And they solve all sorts of problems. And then the parent or the teacher or the older sibling can count the objects and count the actions. And then the child can retell the story, which can then be written up as an equation. And there's total understanding first before the numbers even start to kick in. So this is Brahmagupta's definition of 0. So when the number of positive and negative quantities are equal, the sum is 0. So if we looked at a very simple integer number line from Brahmagupta, we see there's a lovely symmetry here. And the arrows point off in both directions, off to infinity. So you take two red positives and combine them with two black negatives, and they're going to sum to 0. Now, the Indians and the Chinese before them never said negative numbers were less than 0. That absurd idea came into the mainstream in 1685 when John Wallace gave a marching metaphor, and he said that some people had advanced 3 yards less than nothing. Now, instead of advancing 3 yards less than nothing, you've actually retreated 3 yards. So the fact that he chose not to use the word retreat, but to say that some people had advanced less than nothing, just shows that that complexity has just lingered ever since. So one of the secrets to Chinese pedagogy and ancient Bharat's pedagogy, ancient India, is the fact that they had a concept of duality of units. And we think about yin and yang in China, and there are similar concepts in India, where both the units of positive and negative coexisted in the same way that we have north and south and east and west and above 0 and below 0 and so on. But our pedagogy just emerged basically because the British and a few other people really did not understand that the number system from ancient China and ancient India began with the integers. So our ideas that negatives are less than 0 really emerged because we extended the natural numbers to become the integers via subtraction. But the Chinese and the Indians didn't need to do that. And they had a beautiful symmetry and a simplicity to their very empirical, common sense approaches to mathematics, which the West has never to this day ever had. So there's Brahmagupta. He was an astronomer first and foremost, and he did mathematics to support his astronomy. And astronomy was very important in India for predicting the monsoons, the weather, and also for navigation. So in terms of what I've done for this talk, I've looked into the Sanskrit of Brahmagupta, and I've torn it apart line by line, and I've had the help of many Sanskritists decoding this Sanskrit. And then what I've done is I've then done the analysis and then the pedagogical interpretation. So this is kind of like the Bible of mathematics education. It's not in ancient Greek or Hebrew, it's in Sanskrit. And then what I've done is I've pulled out of the Sanskrit various laws or sutras. So you can see here I've got Brahmagupta's 5 addition sutras or addition laws, and there's the original Sanskrit in the top line, and then there's the 5 laws or sutras as documented in the year 628. So we can then start to process things and come up with new concepts like the law of 0 for addition. And you don't know the law of 0 for addition, so that's why I'm excited to tell you. And the law of 0 for addition is what we do to 0 to make an addend. That's what we do to the augend to make a sum. So I'm just going to say farewell and continue on because I need the room on my screen. So we've got augend plus addend equals sum. So the law of 0 that was the law of 0 for addition. We've also got the law of 0 for subtraction, and that's what we do to the subtrahend to make a 0, we do to the minuend to make a difference. So we've got minuend minus subtrahend equals difference. And I'm going to give you examples. I'm just running through the 4 basic laws of the identity elements. The Greeks never had 0 and 1 as numbers, So their foundations never developed with the critically important 0 and 1 in the definitions of their algorithms. Absolutely crazy. So the law of 1 for addition, for multiplication, is what we do to 1 to make a multiplier. That's what we do to the multiplicand to make a product. So it's multiplicand multiplied by multiplier equals product. And then the law of 1 for division is what we do to a divisor to make 1. That's what we do to the dividend to make a quotient. So this is almost like a game of Simon Says, and it's just a patterning game. And I said that before, that mathematics is about relationships between quantities and looking at the patterns that emerge. Well, the fundamental pattern is that there are 4 terms in addition, subtraction, multiplication, and division. In multiplication, we say there are 2 factors and a product, and we've left out the unit, the number 1, which is the critical driver of multiplication on the real number system. And we've got the problem that we have children understand that multiplication makes more because they never understood that multiplication and division are proportional operations as defined by Euclid and as lost by Henry Billingsley in 1570, which is what I argued about with my teacher when I was in grade 2 at age 7. So dividend divided by divisor equals quotient. So the law of 0 for addition, what we do to 0 to make an addend, we do to the augend to make a sum. So let's go to the beach and let's play with a bucket and a spade. And we can see we've got ground level 0, so there are no bricks and no holes. But imagine we've just dug a hole and we've put the sand in our bucket and we've made a brick. So I use these games for children and they love them, and we call them the Happy Harappan brick builder game. And we can introduce integers with this very simply. So here's Podo the puppy. And Podo has her own mathematics, which is why it's called Podometic. And there's another cartoon character called Arith, and Arith created the mathematics that was superseded by Podo the puppy's mathematics. And if you're curious, Podo the puppy is a girl. So yay, girl power. And also Podo the puppy is my own original beagle dog in real life. So we can ask children simple questions. Does this look true or false, or is this silly or real? And Podo's dug a hole and made a brick. And what we have is we have the metaphor for holes as negatives and bricks for positive. So again, we can ask children, is this real or is this silly? And they can say, well, Podo's done 2 holes and she's made 2 bricks. So they'd say that's true. And what about this one? And the children straight away go, no, and they start laughing. And I say, why? And they say, there's only 1 hole. You can't have 2 bricks from the 1 hole. So the children are starting to develop their own integer intuitions here, because what they're realizing is that ground level 0 is being split into an equal number of positives and negatives, which is Brahmagupta's Addition Sutra number 4. So that's true or false? Well, there's a bit of debate about that one, but the children usually say, yes, that's true. And Podo's just simply stacked 2 bricks on top of another. True or false? Well, the children are just gobbling this up, having lots of fun, and we're not doing anything with numbers yet. Mathematics is about relationships between quantities. So let's let children explore relationships between quantities, and then when they understand the physics, then we can start to count. And then we can start to form equations once the intuitions have been locked in. So here's Podo the puppy saying that separate or all together, all my bricks and holes give me 0. And if you count it up, there are 10 red bricks and there are 10 black holes, including the one that Podo the puppy is sitting in. So the law of 0, what we do to 0 to make an addend, we do to the augend to make a sum. So there is an augend, and I hope that you can see this okay. And what we're going to do is we've got 0 underneath the addend. So what we've done to 0, we've added 2. So that's what we have to do to the augend. Boom, we just add 2, and that's the sum. So it's a copying sort of game. So we've got an augend or a number that we start with, and we've got 0 for the addend. So what do we do to 0 to make the addend? Well, we've just added 2 to make the addend. So we've got to add 2 to the augend, and that's the sum. Now, I like to sequence these in a particular way with young children, because it's all about the law of conservation of matter. In children's books, if they have 3 plus 2, they will see 10 objects, because then we have the answer 5 on the page as well. And in the story, you've only got 5 things, and yet the children are seeing 10 things on the page. So I try and keep things a little separate to just help the children be totally focused. So the law of conservation of matter, we can't duplicate quantities in the expression. The most we should see in 3 plus 2 is 5, which I've just said. Now, once we've got the children used to the ideas, then we can drop the idea of the law of conservation of matter a little. So here we've got the augend and the addend, and then the sum. We don't have them all together. So we only ever see a maximum of 5, because that's how many there are as a maximum in the story. So here's the law of 0, where we start to introduce the concept of direct variation. So the law of 0 for addition is what we do to 0 to make our B, that we do to A to make our C. Now, the sutras of the Indians were usually done as shlokas or rhymes. So I often introduce mnemonic or rhyming devices to help children lock in some of these ideas. So what we've done to 0 to make a B is we've added 2. And as you can see down the bottom, in A, we've got a 3. So that's what we've got to do to the A. And that then becomes a 5. So I'll go quickly onto this. You can download this PowerPoint presentation. Just email me after the talk, and it will be available on my website probably in a few days. So here are Brahmagupta's 5 Subtraction Sutras, the Sanskrit across the top, and the various laws or sutras. And the sutra, the Subtraction Sutra number 3 is different to what we've been teaching in the West, and I'll explain that in a few moments. So the law of 0 for subtraction, what we do to the subtrahend to make 0, we do to the minuend to make a difference. So we've got a minuend, which is the first term in subtraction. And what we do to the subtrahend to make it 0, we do to the minuend. So what do we do to the subtrahend to make it 0? We take 2 away. So what do we do to the minuend? We take 2 away, and that's why we get the difference. So what we're doing is we're being very explicit in basing our explanations of the operations on positives and negatives, starting with 0 and 1, because they are the 2 most important numbers in all of mathematics, and they've pretty much been ignored because people thought as identity elements they didn't have a role to play. So here's the law of 0 for subtraction, again, on the chart for direct variation. So when we subtract B to make our 0, then we repeat on A, so C is our hero. So we had 2 for B, which is our subtrahend, as you can see from the key at the top. So as B goes from 2 to 0, A has to go from 5 to 3. So it gets more interesting, because now we move on from the laws of 0 to the laws of 1. Who ever knew there was a law of 1? Okay, so what we do to 1 to make a multiplier, that's what we do to the multiplicand to make a product. So we've got multiplicand multiplied by multiplier. So we've got a multiplier of 3. So what we do to 1 to make a multiplier. So we've got 1 there on display. and we double it to make the multiplier. So that's what we've got to do to the multiplicand. Whatever we do to 1 to make the multiplier, we do to the multiplicand. So we just got to double that, and that's the product. Now I've got some videos on YouTube where I put all of this sort of stuff to music, and it becomes very catchy, and you can see how children can play games with MAB blocks or Cuisenaire rods, where they're actually using 4 terms in multiplication and division. So here we've got multiplying can be fun, you see, do to A as 1 made B. So we always, on the multi-mat, we always have one standard unit in one of these squares. So as 1 becomes 2, 3 becomes 6. And we've moved on from direct variation for addition and subtraction to what I've termed proportional covariation. And here's an example of one of the songs that I first sang at a mathematics conference in Hungary. And feel free to sing along. I've had hundreds of children in India sing this from the music, believe it or not. Multiplying can be fun, you see, do to A as 1 made B. Division, you see, is lots of fun, do to A as B made 1. Multiplying can be fun, you see, do to A as 1 made B. So you've got again a shloka or a rhyme to use with the manipulatives, the multi-mats and the divi-mats, and children can use like integer tiles that you're probably used to, either red or white or black and white. As long as they're 2 different colors, it doesn't matter what it is, and you can start to use these multi-mats and divi-mats to play games of proportion with your manipulatives. So here we reveal, we've got some ratio symbols between the 4 squares. So on the left multi-mat, we see as 1 is to B, A is to C. And on the divi-mat, we see as B is to 1, A is to C. So we can also do it the other way around as well. We can, and this is also a proof of the principle of commutation and commutativity, whereas A is to 1 as C is to B, and so on. So all of these ratio symbols, the 2 dots, reveal the covariation patterns at play between the terms in those squares. So on the very left-hand side, you can see a proportion from multiplication. As 1 is to B, so is A to C. And for division, as B is to 1, so is A is to C. And then when we put numbers on the multi-mat and divi-mat, we can see some instantiations of these devices as well. So as 1 is to 2, 3 is to 6. And in the division, as 2 is to 1, 6 is to 3. And so you have a tool from a sing-song game with manipulatives where you can introduce children to the principles of proportion and 4-termed addition and subtraction when you include the identity elements of 0 and 1. So there are the addition sutras again. So we'll just do some quick run through of some of these sutras or these laws. Very simple. Positive plus positive is positive. That's pretty simple. 4 plus 3 is 7. Negative plus negative is negative. Addition Sutra 2. Addition Sutra 3. Positive plus negative is the difference. Now this one's got a few interesting twists in it. Because you'll start to realize that the red and the black will be able to cancel each other out to become zeros when you are adding things together in this way. And if you think about bumps and holes or bricks and holes, it's a model that children find quite simple to follow along with. So when positive and negative are equal, the sum is 0. So you can see I've circled 3 positives and 3 negatives, and they cancel each other out, which leaves you the 1 positive after you add 4 positives and 3 negatives. And there's a similar example on the lower part of the page. So back to Podo the puppy. Podo has got 7 bricks and she's got 3 holes. So let it rip, Podo. She's moving the bricks over. She's adding +7 and -3. So there she's got 7 positives, or +7. She drops them in the hole, and what you see is what you get. It's a WYSIWYG sort of maths pedagogy where 3 holes and 7 bricks results in 4 bricks, or -3 and +7 results in +4. So these are very simple games, and one of the simple ideas is if you're selling bricks and you've only got 2 bricks and somebody wants to come along and buy 5 bricks, well, you can't take 5 bricks away if you've only got 2 bricks for sale. So what will the happy Harappan child do? Dig 3 holes and make 3 more bricks. And then that child can sell 5 bricks. And guess what's left over? 3 holes. So that's an example of just how simple a pedagogy can be when you start to, and thank you for the comment that just came through. I just realized there's been some chatting going on while I've been talking. Okay, so Addition Sutra 5 is basically the additive identity property of 0. 0 plus positive is positive, and negative plus 0 is negative. So there are the sutras, the Subtraction Sutras. Now, let's apply a couple of them for some difficult problems. And if a smaller positive is subtracted from a larger positive, the result is positive. So if you've got 4 positives, take away 3 positives, it leaves you 1 positive. That's pretty basic. If smaller negative is subtracted from larger negative, the result is negative. So here we've got 5 black minus 3 black gives you 2 black. Now, some of you might actually start to, what's going on here? Because we're saying 3 negatives, or -3, is smaller than -5. You can see it's smaller. You can see it's less numerous. You're seeing the truth, the symmetry of India's maths, where 5 negatives are greater, obviously, than 3 negatives. And this is built into their laws of mathematics. Okay, so if a larger positive is to be subtracted from a smaller positive, the sign of their difference is reversed and positive becomes negative. So we've got 3 positives minus 4 positives. We don't have enough positives. So guess what? We're going to use Addition Sutra 4 and Addition Sutra 5. Addition Sutra 4 is the definition of 0, and Addition Sutra 5 means if we add 0, it doesn't change the number. So we can't take 4 positives away from 3 positives. We can't do it because we don't have enough positives. So what do? Let's add 0. So we add a 0, and there's our 0. We've added 0 in the form of 4 positives and 4 negatives. And whenever we add 0 to a number, it doesn't change its sum. So we can do this. And guess what? Now we can subtract the 4 positives because we've got enough. Here, we don't have enough positives to do the subtraction. So we add 0. Now we've got enough positives to do the subtraction. So we'll do the subtraction. We'll take away the 4 white positives on the right-hand side from the left-hand side. They've gone. And then what we do is we simplify. We simplify by cancelling out the 3 positives and the 3 negatives. And the answer gives you 1 negative. So 3 positives minus 4 positives is 1 negative. That's pretty cool. And yet, there's an even more powerful way of approaching this. So if a larger negative is to be subtracted from a smaller negative, the sign of the difference is reversed and negative becomes positive. 2 negatives minus 4 negatives don't have enough negatives. You cannot take away 4 negatives from 2 negatives. Abstract you can, but in the actual foundations of mathematics you can't without going through the process as documented by India. So we add a 0. So 2 negatives minus 4 negatives, we add our 0. Now we can subtract the 4 negatives. We've got enough. So we subtract the 4 negatives, and then we simplify by removing the 0, and there's the answer of 2 positives. So 2 negatives minus 4 negatives is 2 positives, just up there above my head. Okay, so these are just the negative minus 0, positive minus 0, and 0 minus 0. They remain unchanged. I'll whiz over that. Now, when a positive is to be subtracted from a negative, then it's to be added. Now, we can't subtract 2 positives from 4 negatives. Okay, so we'll add our 0, we'll subtract the 2 positives, and we see that the answer then becomes 6 negatives. Now, here's how we can use the law of 0 to make this quicker and more logical and more direct. The law of 0 is whatever we do to the subtrahend to make 0, we do to the minuend to make the difference. So here we've got 2 negatives minus 4 negatives. Well, we can't subtract the 4 negatives, but guess what? Whatever we do to the subtrahend to make it 0, that's what we do to the minuend. So how do we make 4 negatives 0? We add 4 positives. And because we added 4 positives to the 4 negatives to make them 0, we add the 4 positives to the minuend, we cancel out the 0, and we get the answer of 2. So if you use the law of 0, it doesn't matter the sign of the terms in the expression. The law of 0 is on your side. Okay, so I'm going to quickly go through the remainder of the slides. We've only got around about 5 minutes left. I've been having maybe too much fun. So here we're going to see a proof of the product of 2 dashed numbers, or 1 negative number and 1 subtractive number is positive. So via Brahmagupta, we multiply positives and negatives by either adding to 0 multiple times or subtracting from 0 multiple times. So on the left-hand side, we've got negative a multiplied by plus b. And on the right-hand side, we've got negative a multiplied by minus b. Now, the sign of the adjective is superscript, and the sign for the verb is normal case. So negative a multiplied by plus b is negative a added to 0 b times. Negative a multiplied by minus b is negative a subtracted from b 0 times. This is actually how mathematics works. So with integral multiplication, a is the adjective describing counts or measures of noun quantities, and b is the adverb describing verb counts of additions or subtractions. And don't worry, your head's exploding with all this information. Don't worry, email me and you'll get a copy of the PowerPoint presentation very, very shortly. So negative a multiplied by minus b, or subtraction b times, equals negative a subtracted from 0 b times. And negative 1 multiplied by minus 1, it's not negative times negative. It's not minus times minus. The actual structure of the mathematics is it's negative 1 subtracted once from 0. Now, this is the normal way that you go about proving negative into negative is positive, and it's a bit of it explodes your brain a little bit. And I wrote this one up in for a magazine back in 2015. not going to show it to you now. I'm just showing you how complex it is. Now, negative a multiplied by minus b, or negative 1 multiplied by minus 1, is actually just negative 1 subtracted from 0 one time. So I've got two schematics of 0. I've got positive 1 plus negative 1. That's the symbolic representation, the numeric count of 0. And then I've kind of got the integer tile approach, where we've got one circle with a positive, and we've got one circle with a negative, and they're the opposite colors inside a 0. So if we wanted to multiply negative 1 by minus 1, we subtract negative 1 from 0 and look at the answer. Sorry. So we look at the answer, and guess what? The answer is positive 1. You missed it. It was so quick. There's 0. We've got a symbolic 0 of the digits positive 1 and negative 1. We take away negative 1, it releases positive 1. Inside the green 0 circle, we take away the negative 1, it's going to leave the red circle positive 1. So negative 1 subtracted once from 0 has to be positive 1. So that's a kind of a Sanskrit-based demonstration or instantiation of the laws of maths compared to the Western demonstration, which you'd be doing in middle high school perhaps. So the children who are at grade 1 and grade 2 will understand how to play the games where they're subtracting integer tiles from 0. And if they don't have enough, they just add a 0, and they can have as many 0 pairs as they want. So we've pretty much come to the end of our time. I'll just whiz through the next few slides just to let you know that there's some things that you can download. What I've written up is I've written up a kind of a variation on the Cartesian plane, and I've called it the Brahmaguptan Plane, and it encapsulates positive areas and negative areas. Sounds very strange. How can you have a negative area? Well, it's very simple. If Thales went to Egypt and had met fishers, people who fished for a living instead of farmers, they might have been interested in the area of water for the people who were doing fishing to cast their nets. And for the fishers, the fishermen, fisherwomen, the area of water that they had to cast their nets would have been positive, and the area of land would have been negative. But for the farmers, here's the beautiful symmetry of physics. For the farmers, the land would have been positive area, and the water, like the flooding of the Nile, would have been the negative area. So you can actually start to bring back the concepts of symmetry from even ancient Egyptian mathematics. It's just that no one developed the pedagogy, and so that's what I've been doing. So you can download that paper at that web address, and there's a few slides here where I explain the concepts of how it all works. And you can see you can have positive and negative areas, and all the actual nuts and bolts of exactly what you do becomes a common sense game for children to play. So you get this sort of grid, which is like the 4 quadrants of the Cartesian plane. And that's the extract of paper on the Brahmaguptan Plane. And there's more whizzing here we just don't have time to go into. But email me, and I'll just get to the final slide where, okay, there's the address. Email me your thoughts about this presentation. I'd love to get some feedback from you. It's simply feedback at Podo, the name of my dog that led to Podometic, feedback at podo.in. Send me your thoughts about this presentation. It's been my first one in North America. I've been so happy to be able to present for the Association of Maths Teachers of New York State. I hope that you all remain happy and healthy, and may whoever you voted for in the election be a great positive influence for the world for the next 4 years. My name has been Jonathan Crabtree. My website is podometic.in or podometic.com. I've got dozens of papers and slides and videos all available absolutely free of charge. I can't stop doing research. I don't earn any money from it. I've been doing this with every cent I've got, and I'll be doing it for as long as I live. Thank you very, very much for being my first audience. I would love to get your feedback. Goodbye, farewell from Melbourne, Australia.